And the last speaker for the session and the conference is Peter McGill from the Livermore National Laboratory. And the talk, too many things to handle, is Probing the Stellar Graveyard and Dark Matter with Astrometric Microlensing.
Okay, can we all hear me? Thumbs up. Okay, I'm going to assume that people can hear me. So yeah, thank you for having me. So yeah, I'm Peter McGill. I'm a postdoc at Lawrence Livermore National Lab. And I'm going to be talking about astrometric opportunities with Roman. I'm benefiting coming after a string of really good microlensing talks that covered the basics, so we should be all excited about microlensing and know roughly how it works. So just to put, well, excellent.
It should be up.
Okay, cool. Yeah, so just to put the talk in context, we are in the golden astrometric era. I don't think it's going to get better than the next 5 years, next 10 years. We have Gaia that's just about to complete its decade-long survey of the entire astrometric sky. We're going to have the Roman galactic bulge time domain survey that's going to provide precision astrometry over the next 5 years. And then we also have, HST, James Webb, possibly Euclid as astrometric follow-up resources. So we are in, I think this is the golden astrometric era. It is not going to be better than this ever again. So as you've heard, microlensing, the kind of unique niche of microlensing is we get a window into the dark and isolated galactic populations. So we don't need any flux from the object we need to study, and we don't need to have it, it doesn't need to have a companion. We can actually extract things like mass, distance, and velocity distributions for dark objects in the galaxy. And it is really the only viable way to detect dark and isolated objects. So this is microlensing's real niche and power. And so, as you've heard from Casey and various other people, there are two effects that can arise from microlensing. Although they come from the same underlying lensing phenomenon, the different signals have very different characteristics. So the familiar photometric effect, the transient brightening of the source, basically lasts days to months, even hours for planet mass things in the galaxy. And this signal you can almost make it arbitrarily large for bringing your lens and source closer together. You eventually get washed out by higher order effects, but the closer you make lens and source, the larger it gets. There's also the astrometric signal, which is the transient deviation of the source position as a function of time. So these are a lot longer. The astrometric signal dies off a lot slower with lens source separation compared to the photometric signal. And these signals are actually fundamentally limited by the size of the angular Einstein radius of the system. So it's quite different to the photometric signal. And these signals aren't necessarily temporally located. In the simplest case, the astrometric signal can actually peak before and after the photometric peak. So there's this like temporal incoherence between the signals. So these different characteristics actually lead to these like 3 different niche detection channels that are possible. So the Roman Galactic Bulge Time Domain Survey with its microlensing exoplanet science requirements is almost entirely focusing on using the photometric signal exclusively to deliver the science requirements. So they're going to probably use some auxiliary information, but most of the physics is going to be extracted from the photometric signal. But there are actually regimes where you can detect photometric and astrometric signals together. So this was an example of this was the detection of the first isolated black hole. So this relied on detecting photometry on the ground and the astrometric signal from HST, which is critical to actually determine the mass of the lens and the identity. But there's also this regime where the lens and source are so widely separated that there's no photometric signal at all. So there's a regime where you can bring your source out so far that there's no photometric amplification and you just get a detectable astrometric signal with Roman. So this is the regime that I want to talk about today, which is completely complementary to all of the microlensing regimes that have been talked about so far. So I can start by discussing this regime in the context of primordial black holes and dark matter. But if you're not interested in that, you can think of this as kind of like a test mass case, injecting things into a full Roman galactic bulge time domain area simulation and seeing how sensitive this pure astrometric regime is to being detected. So you can see we did this full simulation, just basically extracted only astrometric events, so these wide separation, hardly any photometric signal at all. And you can see for like reasonably small fractions of dark matter, you get quite a number of detections in this channel. And so the thing that you can extract from these events the useful things is this Einstein timescale, which is the time of the event, and the angular Einstein radius, which is, you can basically think about that as like the size of the astrometric signal. So you can see as you increase your masses, the events get longer and the astrometric signal gets bigger. As you decrease them, the opposite is true. And what's really interesting, so we can think of this, as like kind of like a test mass case, is that the different distances this probes. So if you inject something that's kind of planet mass into the simulation, that top panel, the distance, you actually probe a very small distance from the observer for detecting events. So this is because your lens is so small, it has to be very close by to produce a large enough theta E to be detectable by a Raman. And then the opposite is true for large mass events caused by very heavy lenses. So you're almost exclusively sensitive to things that are far away. And this is because of this long time scale of the astrometric signal. You actually don't see enough of it change enough within the 5-year survey to actually detect anything. So there's this like interesting distance probe that you get. And if you turn these into dark matter constraints, the Roman Galactic Bulge Time Domain Survey, purely astrometrically, is going to fill in this very interesting notch of the mass fraction of dark matter space that hasn't really been probed before. So now moving on to the more interesting things, the arguably more interesting things of the astrophysical population. So your stars, your white dwarfs, your neutron stars, and your black holes from the simulation. So if you run, you factor in the cadence, you do all the work to make sure your simulation is accurate. The yield of black holes of this purely astrometric regime, which is completely complementary to what's been done before, is actually the same kind of order as this photometric plus astrometric regime, which is in Casey's core community survey white paper on black holes. So this kind of regime is, in terms of numbers of detected black holes and neutron stars, is going to be as important as the photometric and astrometric regime. And on the right here, some of the interesting stuff we're writing up at the moment is that if you look at the simulation, you plot this event timescale versus astrometric signal, then neutron stars end up in a unique region of the space, which means that Roman is probably going to be able to say something pretty strong about the isolated neutron star population. And this is from purely astrometric signals only. There's no photometric signal here. And so the other thing you can start to do, right, if you go back to this photometric astrometric regime, and because of the signals are not being temporally located, you can actually, there's kind of real-time decision making you can do to kind of optimize and increase the yield of lenses. So we get the astrometric signal before the photometric signal for a certain class of lenses. Is that useful information? Can we use it to make a real-time decision about how to, synergize with other surveys? There's lots of talk about, photometric synergies between ground-based surveys. We should also be thinking astrometrically, like how can Roman astrometrically help ground-based surveys? And basically all this science relies on there being some kind of real-time astrometric processing of the Roman data stream. That's really key to kind of doing this interesting kind of real-time decision making with astrometry. So just summarizing, so there's going to be about 1,000 events in this pure astrometric regime where we don't see any photometry whatsoever for microlensing. We're probably going to get a novel dark matter constraint with the Galactic Bulge Time Domain Survey. And there are plenty of opportunities to think about synergies astrometrically and photometrically. I suppose the real thing that would really accelerate this kind of science is, if Roman were to be able to study the transient astrometric sky, which has never been done before. So looking for things that are accelerating astrometrically. So the Gaia Science Alerts team really wanted to do this, but they ran out of time. And this is a massive missed opportunity. And they produced photometric alerts, and there was a big push to try and do accelerating sources to be followed up, but they never got round to it. So I think this is a potentially exciting and huge opportunity for Roman, but of course it's hard, and we need to figure out how to do it. And that's it.
Peter, for finishing even before your time. So questions for Peter. Very nice talk. Julie.
Would Roman be able to constrain, would microlensing searches for neutron stars help constrain the population of millisecond pulsars towards the galactic center?
Yeah, I've not thought about that. probably. The main thing that pushes them out into this unique space is the kick velocities. So we think that there's going to be a good number density estimate, but mainly it's going to be able to constrain the kick velocity distribution of the neutron stars.
And part of the reason that I ask is that millisecond pulsars are one of the candidate sources for the origin of the Fermi gamma ray excess at the galactic center, but dark matter also is. So it would be quite helpful if Roman could help distinguish between those two scenarios.
Interesting.
Winky, what idea?
Did you work out the difference between the astrometric and the photometric signals as a function of the different types? Like how much more soon, for each of your types of signals? It'd be interesting to see the delta T's. I know you had the cartoon of it, but
Yeah.
you
No,
actually
that's-
see the distribution of the delta T's to then see what.
Yeah, no, that's a really good point. Yeah, I've not done those calculations in detail, but yeah, that's critical. I mean, yeah, depending on this time lag, it might give you opportunity to trigger up other follow-up resources to deal with things. But yeah, it's going to be longer the more massive the lens is. This delay between the photometric and astrometric peak.
Right here.
Thanks for the great talk. Maybe this is a question for the Roman team, but with the data being immediately public, how does things like astrometry or things that require extensive, modeling of multiple epochs work? Like, is there going to be like a live feed of astrometric catalog, or is this going to be released at one time? But I'm not sure where this is. It's just directed through the 4Pi sky.
So I mean, the reason I'm pausing is that there is a plan for a relatively immediate level of processing, and then after some logical definition of a survey, which is going to be sort of observation dependent, there will be a more final calibrated high-level analysis that might be closer to this is for all the data that is not the galactic bulge time domain survey. And I think somebody from the SSC should probably address the data release plans for that.
So there is a plan to deliver astrometry and photometry for all the stars that are in the catalog. Oh, so there is a plan to have astrometry and photometry for all the stars in the catalog for the monitored in the toward the galactic bulge. There is, however, no plan for doing astrometric microlensing.
A marathon.
So the astrometry in the the galactic bulge time domain survey fields is important for getting good photometry because the the higher angular resolution means that we're much more sensitive to relative proper motion between different stars, possibly contaminating the photometry. So we're going to have regular astrometry coming both from its 8-day stacks of sort of convolved images. We'll have astrometry from that, and then the Argus Pit has requested image cutouts for all the microlensing events that we found, and so those are should be a good tool to do astrometry, although there's not necessarily a plan to, do to process all the astrometry. But one thing that the individual images is important for is astrometric microlensing of binary microlensing events, because those can have shifts on very rapid timescales where you create new or destroyed images, which can happen, in a timescale of an hour or less. So, so there are a lot of possibilities for getting astrometric microlensing data out. It might possibly be a good proposal for the next wide field WFI science from Oman. I'm not sure when the next call is supposed to be coming out, but I think it's not very far away.
But there's two regimes here, right? There's a regime where you might want astrometry or the astrometric signal to make a real-time decision about what to do next. And then the regime that you're talking about where you're going to figure something out offline, right? About some binary event that you're going to process the astrometry later for. So I think there's a couple of different use cases.
Well, I mean, I think these image cutouts should be available pretty rapidly.
And at what cadence will the astrometry be available? Like the images or
the images would be available, and their cadence is 15 minutes.
Well, I was going to change topic slightly. We've had in the last month or so a couple of people step up to volunteer to lead an astrometry working group for Roman. So we will proceed to set up that group. So what I would recommend is that you join it and join the fun.
Thank you so much. Let's see if there is. Okay. Well, thank you so much, Peter, again.